Welcome to another module in this massive open online course. So, in this module let us start looking at the Fourier transform. The Fourier transform, remember we are looking at the spectra of signals, and we said the spectra can be of two types. One is the discrete Fourier series, which is for a periodic signal, and the other one is the Fourier transform, which is defined for an aperiodic continuous time signal xt. So, let us start looking at the Fourier transform. Which we can abbreviate as FT, the Fourier transform, and remember this is for the spectrum of an aperiodic this is for the spectrum of an aperiodic continuous of an aperiodic continuous time signal xt, that is a signal xt. Remember previously looked at the spectrum, that is a discrete Fourier series of a periodic signal xt. Now, we are looking at the Fourier transform, which gives the spectrum of a continuous aperiodic time signal xt. Alright. So, let us consider a signal xt, then its Fourier transform xf. Alright. So, xf, which is the Fourier transform of xt, this is given as the integral. So, let us start by writing consider an aperiodic signal xt, its Fourier transform or its Fourier transform x of f is given as the Fourier transform x of f is given as x of f equals integral minus infinity to infinity x of t e power minus j 2 pi f t dt. Okay. So, this is the signal, this is the Fourier f is the frequency, f is the frequency, okay, all right, and we denote the signal xt, that is the signal xt and its Fourier transform. These form a Fourier transform pair and it is denoted by this symbol. So, this forms the, we call this xt, signal xt and its Fourier transform as a Fourier transform pair, that is the signal xt and a signal x capital Xf as the Fourier transform pair. Remember the signal xt is in the time domain, capital Xf is in the frequency domain, these are two totally different domains, alright. So, the signal xt, let us also note that the signal xt, this is in the time domain and this is in the frequency domain, xf is in the xt is in the time domain, xf is in the frequency domain. And note, look at this, even though xt might be real, but this is a complex quantity. In fact, e to the power of minus j 2 pi f t, this is a complex sinusoid, alright. So, the Fourier transform xf is in general a complex quantity. So, xf is in general complex, alright, and therefore, we have two components of xf, one is the magnitude. So, I have the magnitude, this denotes the magnitude spectrum, then we have the angle, that is the phase of xf, which denotes the so we have the magnitude spectrum and we have the phase spectrum. That is, if we consider the magnitude, xf is in general a complex quantity, the magnitude of xf denotes the magnitude spectrum, the phase of xf denotes the phase spectrum. Okay, all right. And of course, now what we have found so far is, given xt, how to find the Fourier transform xf in the frequency domain. Of course, we are also interested in the inverse problem, that is, given xf, how to find the, given the Fourier transform capital Xf, how to find the corresponding time domain signal, and this is given through the corresponding inverse Fourier transform. So, what we have shown is, given xt, how to find xf, and now what we are interested in, given xf, what is the corresponding time domain signal xt, and we are saying this is given by the and this is given by the inverse Fourier transform, the IFT. The inverse Fourier transform can be defined as follows, that is, the x signal xt corresponding to xf is given as integral minus infinity to infinity xf e to the power of j 2 pi f t dt, and this is simply known as the expression. So, notice that for the Fourier transform, we have an e to the power of minus j 2 pi f t. For the inverse Fourier transform, we have an e to the power of j 2 pi f t. This is the expression for the inverse. This is the expression for the inverse Fourier transform. Okay, so, what we have is, we have basically we have defined the Fourier transform, which gives the spectrum of a continuous time a periodic signal x t, and we also defined, or we also shown how to derive the expression for the continuous time signal in the time domain given the Fourier transform in the frequency domain. That is, so the Fourier transform of the continuous time signal is given by the expression for the Fourier transform. The time domain signal from the Fourier transform, that is capital Xf, is given by the inverse Fourier transform. All right. So, let us now do a simple example to compute the Fourier transform. Okay. So, let us now do a simple example to compute the Fourier transform. Okay. Consider consider the pulse x t, which is defined as, we have a pulse x t which is defined as p t of t, which is equal to, let me first draw the signal in the time domain. It is a pulse of width capital T, which can be represented as follows, that is the pulse of height unity from minus t by 2 to t by 2. So, the width of the pulse is capital T. So, basically, and this is outside of this window of size t, this is 0. So, this pulse p sub t of t is 1 for magnitude of t less than or equal to t by 2, that is t lying between minus t by 2 to capital T by 2, and 0 otherwise, all right. So, this is a pulse or a rectangular window. You can also say a pulse is nothing but a rectangular window. So, this is a pulse of width t, height equal to 1 centered at, all right. So, this is centered at 0, all right. So, this is a pulse of width capital T or duration capital T, height unity, all right, and centered at 0, which means it spans minus capital T by 2 to capital T by 2. This is a very simple signal, and of course, is of lot of relevance in communication systems. We are going to look at the relevance of this in the coming modules, all right. This is a very simple signal which arises fairly frequently, all right. It is a pulse of height 1 and width capital T, all right. Let us now find the Fourier transform of this signal P sub capital T of t, okay. And we know the Fourier transform, we have shown the expression earlier, that is x of f is given as minus infinity to infinity x of t e to the power of minus j 2 pi f t dt, and x of t is non-zero only from minus t by 2 to t by 2, in which it is 1. So, let us write this as, let us first substitute p of p sub t of t e to the power of f t dt, and p sub t of t, remember this is non-zero only from minus t over 2 to t over 2, in which it is 1 e to the power of minus j 2 pi f t dt, okay. And this integral, this is your, you can call this also as the Fourier transform of p t, that is p t f, and the integral of e to the power of minus j 2 pi f t, this is e to the power of minus j 2 pi f t divided by minus j 2 pi f evaluated between the limits t by 2 to minus t by 2, okay. And now substituting the limits, we have e to the power of minus j pi f t by 2 minus e to the power of j pi f t by 2 by minus j 2 pi f and this is equal to, now e to the power of minus j, e to the power of minus j 2 pi f t by 2 minus e to the power of j 2 pi f t by 2. This is basically minus 2 j sin 2 pi f t by 2. Okay. So, this is nothing but, so this is e to the power of, I am sorry, there is a 2 pi missing over here, this is minus j 2 pi f t by 2. So, this will be minus 2 j sin 2 pi f t by 2 by minus j minus j 2 pi f the 2j minus 2j minus 2j cancels, and what we have, and of course, the 2 here goes. So, what we have is sin pi f t divided by pi f. Okay. So, this is the expression for the, this is the expression for the Fourier transform. This is Fourier transform of your pulse or rectangular window PTT, and remember we can also say this as your PTT and its spectrum PTF. These form a Fourier transform pair. These form a Fourier transform pair. And in fact, now I can also write this PT of f as follows, that is PT of f, which is sin pi f t by pi f. I can multiply in the denominator by capital T, numerator by capital T, and I can now write this as I can now write this as T sinc f t, where basically this function sinc of x, this function, it is a very interesting function and arises frequently in communication and signal processing. This is defined as sin pi x, this is defined as sin pi x over pi x. So, I can conveniently write this using the sinc function. This is colloquially, this is simply called the sinc function. I can write this as capital T times sinc f capital T, alright, where capital T is the duration of the pulse. Sinc denotes the sinc function, where sinc of x is sin of pi x divided by pi x. Okay. So, this is simply known as the sinc, and it is useful to know the definition of this function, because we are interested, we will frequently keep referring to this function, which is a sinc function, that is sin pi x by pi x. Therefore, it is useful to know the definition of this function. Now, look at this, the sinc function, look at the properties of the sinc function. The sinc function at x equal to 0, if you take the limit extending to 0 of sin pi x by pi x, or let us say limit extending to 0 of sinc x, sinc of 0 is defined as limit extending to 0 of sinc of x, which is equal to a limit extending to 0 of sin pi x by pi x, and this is equal to 1. So, people simply say that a sinc of 0 is simply set as equal to 1. So, sinc of x at x equal to 0 is simply set as 1, because although it is not defined, strictly speaking it is not defined at 0, because sin x by x at x equal to 0 is undefined. So, we consider the limit as x tending to 0, and therefore, the sinc of x at x tends to 0 as sinc of 0 is basically 1. And further notice that sinc of x, which is sin pi x which is sin pi x equal to 0 if sin pi x equal to 0 implies pi x equals any multiple of k times pi implies x equal to any integer k other than k not equal to 0. So, sinc x at x equal to 0. So, at x equal to 0 we have sinc of 0 equal to 1, except that at all other integers x equal to k, sinc of k would be sin of k pi divided by k pi, but sin of k pi for any integer k is 0. So, this is 0. So, for all integers k not 0, the sinc of x, that is sinc k for k any integer is 0. Okay. So, therefore, now look at this, we have our function pt of f. Now, let us go back using these properties. Your pt of f equals t sinc of f t if at f equal to 0, this becomes t times sinc of 0, this is equal to t. At f equal to any k over t, we have t sinc f times k over t equals t sinc k equals 0. So, at f equal to 0, the frequency response t sinc f capital T is equal to capital T. At any other f such that f equals k over t, that is multiples k of the inverse duration, that is k over t, where t is the duration of the window. At all multiples k, at all k over t, where k is any integer other than 0, the frequency response is 0. And if you can look at this, let us go back and look at this. This is t sin pi f t by pi f t. So, this looks like a sine, except so this looks like sin x, except amplitude is constantly decreasing due to this factor amplitude is constantly decreasing due to this factor 1 over f. So, amplitude is decreasing. So, how does this look? Let us try to plot this sinc function. If I plot this function t sinc f t, in the frequency domain, this function looks as, this is the frequency axis, this is the amplitude, and I will have at f equal to 0, this is t, and then it will have an amplitude that is continuously decreasing. And these points, so here it is t, this is 0, and these points where it is 0 are integer multiples of 1 over t. So, this is 1 over t, 2 over t, the first null on the negative axis is minus 1 over t, minus 2 over t, that is integer multiples of minus 2 over t, and therefore, if you look at this sinc function, it has a decaying envelope, and if you look at the null to null bandwidth, that will be minus 1 by t to 1 over t. So, the spacing in the frequency domains, the spacing on the frequency axis between the nulls on the negative, the first null on the negative frequency side, first null on the positive frequency, this is known as the null to null bandwidth, that is 2 over t, where t is the duration of the pulse. Alright. So, this is our frequency axis, this is our amplitude axis, 2 over t is the null to null. There are many notions of bandwidth, this is known as the null to null bandwidth. Alright. So, this is the, so these are basically, if you can see, these are basically the nulls. Okay. So, these are the nulls. In fact, there are several nulls. In fact, at every multiple of k over t, in fact, at every multiple, integer multiple of 1 over t, that is k over t, this is 0, except when k is equal to 0. At k equal, at f is equal to 0, this is, as we already seen, this is capital T. Alright. So, this is t sinc f t, and this is, so we can say our pulse p t of t, and we have now its Fourier transform pair, which is t sinc f of t. Alright. And this sinc function has very significant, has a lot of applications in communications, and is very fundamental, is of fundamental importance in communications. Alright. So, this is basically, this is given by the sinc function, the Fourier transform of the pulse is given by the sinc function. Alright. So, in this module what we have done is basically we have defined the Fourier transform of a continuous time aperiodic signal, the inverse Fourier transform of, that is given the Fourier transform, how to derive the time domain signal, and also illustrated the computation of the Fourier transform, through an example. And just to conclude, remember, one can also now say that using the inverse Fourier transform, we have p t of t will be, it must follow that p t of t is the inverse Fourier transform of p t of f, and therefore, you can say that integral minus infinity to infinity t sinc f t e to the power of j 2 pi f t will be p t, that is your time domain. This is back, gives back your so this must give back the time domain pulse. Alright. So, if you take the Fourier transform p t of f in the frequency domain, compute its inverse Fourier transform, you must get back the time domain pulse. Alright. So, we will stop this module here and look at other aspects in the subsequent modules. Thank you.